right, we're going to start talking about how we can determine the convergence of series using a bunch of different tests. In this video, we're just going to take a look at the first two tests, but by the end of this unit, you will learn a whole bunch of them. So just to recap a couple of things from pre-calculus, usually we have a function, we say y is a function of x, where x is usually like maybe all real numbers or some subset of real numbers. We're going to take that and just sort of modify it a little bit. We're going to take a look at a sequence, which just means that our domain is now the set of natural numbers. So like 1, 2, 3, 4. A lot of times we call these discrete functions. That just means that we're not really going to have a nice continuous function when we graph this thing. It's usually a series of dots. So the notation we usually see a sub n equals a sub 1, a sub 2, et cetera, et cetera. And the output, we don't typically refer to as the y values. We're going to usually refer to them as the terms of a sequence. Now, if I take the terms of a sequence and then I start adding them together, I get a series. So a series is another sequence itself where the terms are generated by adding what we call this the partial sums, or adding parts of the other terms or the terms of another sequence. So for example, if I have a sequence here, if I want to look at a series associated with that sequence, the first term would just be the same as the first term of my sequence. The second term of the series would be the sum of the first two. The third term would be the sum of the first three, so on and so on and so on. And often what we're actually going to use is sigma notation. So you should be familiar with this from pre-calculus. So we care about convergence or divergence. Convergence for us is going to mean that we can evaluate a particular limit. So for any sequence, this includes series, since every series is a sequence, we say that it converges to a number c if the limit as n goes to infinity is actually that number c. So for example, if I look at this sequence of numbers, it seems like if I keep going, the limit will be 0. So this would converge to 0. Now, the first test we're going to learn for the convergence of series is something you actually already saw in pre-calculus. We're going to call this the geometric series test. So your geometric series are usually series. They're kind of like exponential functions, except again, you're only putting in whole numbers starting from 1. Sometimes we start at 0, but we usually start at 1. That number that we're raising the powers, we usually call the common ratio. And that common ratio is going to determine if we diverge or converge. Now, if that common ratio is bigger or equal to 1 in absolute value, we do not approach anything, meaning the limit as n goes to infinity of the series is not going to exist, or it'll go off to infinity or minus infinity. Could be one of those three scenarios. Now, if the common ratio in absolute value is less than 1, it'll always approach a value, which is this one right here, a divided by 1 minus r. So let's take a look at, say, this series right here. This is geometric because I have a number multiplied by something raised to the power of n. Now for this one, my common ratio would be 2/3. That's my base there. So if I look at that, r equals 2/3. The absolute value of that is 2/3, which is less than 1. So absolute value of common ratio less than 1. That tells me that this is going to converge. Furthermore, since this is geometric, it converges to the first term divided by 1 minus the common ratio. So in this example, it looked like it would converge to 15. What that means for us is if we were to actually add 5 times 2/3 to the 0 plus 5 times 2/3 to the 1 plus 5 times 2/3 squared plus ... off to infinity, you actually get really, 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 really close to 15, so close that you can't actually tell the difference. Now, if I change that a little bit, say 4/3, now my common ratio is 4/3. I still have that 5, but my common ratio has changed. Its absolute value is bigger than or equal to 1, which means this is going to diverge. So that's your first test, the geometric series test. It's all about the common ratio. The second test is called the nth term test for divergence. I cannot stress that part enough. Divergence. This only works to show that a series diverges. You can never, ever, 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 ever use this to show that a series actually converges. It doesn't work that way. It can only show that it diverges. So your series will either converge or it will diverge. If you can show that it diverges, then you don't have to show that it may or may not converge. So how does this test work? Well, if you take a look at um, the sequence that you're adding the terms of to generate your series, if the limit as n goes to infinity is not a zero, then automatically you can say that the series is going to diverge. If it does equal to zero, we would just say that the test is inconclusive and we have to try something else. So let's say I have this series right here. If I take a look at the sequence inside that I'm adding all of the terms of, 4n cubed plus 1 divided by 7n cubed plus n minus 2, if I take a look at the limit as n goes to infinity, this is really just like a rational function. That's going to be the ratio of leading coefficients, since the powers or the leading coefficients they're attached to powers of my variable that are equal, n cubed and n cubed. So that becomes 4/7. That is not equal to zero, so that tells me this is going to diverge by the nth term test for divergence, because again, the limit is not zero. Now, if I change that up here, if I change the power of my numerator to just 4n, here, if I take a look at that limit, I get a zero. And so you might be tempted to say, oh, it's zero, so it's going to converge. A few seconds ago, I just said, you cannot use this to show convergence. So at this point, we would just say, the test is inconclusive and we got to try something else. That'll actually do it for this video.